So we have discussed the adiabatic process with some examples in the previous session. Let me give you some more examples of adiabatic process that occurs in nature. I told you that adiabatic processes can be realized either by ensuring perfect insulation between the system and the surrounding such that no heat enters or leaves the system. The other method is by making the process to happen suddenly or very quick. So in the figure given here, you can see there is a cylinder and there is a piston which is movable, and inside this cylinder we can keep a very small piece of cotton which will get ignited or it will undergo combustion very easily. Now when we compress this piston all of a sudden by giving a sudden push downwards, you can see that the cotton that you have kept inside the cylinder will be getting ignited, and that is what is shown in the second diagram over here. And there won't be any combustion of the cotton piece inside the cylinder if you press this particular piston slowly, and you can understand why it happens so. Once you are doing the process slowly, of course you are doing work on the system, means the gas inside this cylinder will be getting compressed for sure, but the work done is in such a slow pace that the energy or the internal energy increase of this system will be causing a rise in the temperature of the system, and heat will get dissipated or it will be getting transferred to the surrounding. Whatever heat is generated, that will get leaked out into the surrounding, such that the increasing temperature of the system will be insufficient to cause ignition of the cotton that you have kept inside. Whereas when you do the process in a sudden manner, you thrust the piston downwards all of a sudden, the compression happens so fast such that the process is adiabatic, means the heat generated inside the system will not get enough time to leak out of the system, and the rise in temperature will be huge to cause ignition of the cotton. So this is a very simple illustration of the adiabatic process, and especially adiabatic compression that results in heating. So I have concluded here that an adiabatic compression will result in heating. Now the same process is actually employed in a diesel engine. You might have learned about two types of engines, the diesel engine and the petrol engine, and in the design of diesel engine there is a major difference with that of a petrol engine. In a petrol engine we will be using a spark plug to begin the ignition. There is what is known as an ignition stroke in the working of a petrol engine. But in a diesel engine we are not using a spark plug for causing the combustion of the fuel. Instead, we depend upon an adiabatic compression of the mixture of air and diesel inside the cylinder of the engine. You will see that in the case of a diesel engine, the diesel air mixture taken into the cylinder will be compressed so quickly so that the temperature increases enormously and it produces a spark by itself. There is no need of any external spark plug in the case of a diesel engine. So that can be taken as a practical application of the fact that adiabatic compression results in a rise in temperature. Then we come to another example of adiabatic process in nature. Maybe it will help you to understand the weather, or you can also see that how clouds are formed. Formation of clouds is yet another example of an adiabatic process. Here I have explained adiabatic compression. Now let us discuss about adiabatic expansion. You know that the air just above the surface of the earth is usually getting warm, and warm air will be undergoing expansion, and the expansion is purely adiabatic in nature. Now you know why it is adiabatic in nature. The pressure varies with altitude. You know, the pressure varies with altitude. You have got higher pressure at lower altitudes, and as you go above and above, you know, like you move on to the mountains, the pressure will be dropping down. Now, so there is a pressure gradient with height. So the pressure decreases with the height, P decreases. I can mark it like this. And you know that the temperature near to the surface is more, so temperature also will be reducing. You can see that, and you can see as expansion happens, the volume will be going on changing. So can't you see that in the process that we are describing, the pressure changes, the volume changes, and also the temperature changes. So we say that the process is an adiabatic process. Now what happens is that when the warm air is rising from the surface of the earth upwards, it will be undergoing an expansion, and as a result of the expansion, the water vapor inside this parcel of air, it will be cooling down, and it will condense into water droplets, and finally it will form what is known as clouds. So you can see clouds are formed due to the condensation of water droplets that is present in every parcel of air that rises from the surface of earth upwards. And it's in general found that the temperature of a parcel of dry air, means a bunch of dry air, decreases at the rate of 10 degrees Celsius for every 1 kilometer of elevation in the atmosphere. So I have shown an adjacent figure here. Consider the temperature near to the surface of the ground is around some 25 degrees Celsius. If you see if you observe the temperature of a bunch of air, or better you call it as a parcel of air, and remember this parcel of air may be having size of the order of maybe some meters, or sometimes it is a few kilometers. So when this parcel of air has just moved to say some 1 kilometer in the atmosphere, you can see that the temperature would have got reduced by some 10 degrees Celsius. So a 10 degrees Celsius of temperature decrease would occur for 1 kilometer of elevation above the surface of earth. Now once again, when this patch of air has reached 2 kilometers above the surface, you can see again once again there is a reduction in temperature of 10 degrees Celsius. So it has now reached 5 degrees Celsius, and again 3 kilometers maybe it has gone below 0 degrees Celsius to some minus 5 degrees Celsius. Then once again at 4 kilometer above the surface of earth, the temperature of this patch of or parcel of air would have reached some minus 50 degrees Celsius, and you know at these very low temperatures water droplets would have started to form thick, and it becomes what is known as a cloud. So formation of cloud is yet another example of a natural adiabatic process. You can read about these topics in detail. Those who are interested in some sort of meteorology, etc., you can refer to these topics, and you'll be able to understand the role of thermodynamics in predicting the formation of the kind of clouds as well. And remember, this is one career prospect for a student of physics. Once you complete your degree in physics, you can even divert to related fields like meteorology, oceanography, etc. And there are certain courses in institutes like CUSAT, where you can go for an MSc in meteorology or MSc in oceanography, etc., where you will find the practical applications of the laws of thermodynamics, what you learned in your UG curriculum. So hope you will explore more if you have time to spend on that one. So that's about the examples of adiabatic processes. So to summarize, I told you adiabatic processes are those processes in which no heat transfer occurs between the system and the surrounding. Usually there are two different ways to make a process adiabatic. Either you insulate the system perfectly from its surroundings, or you make the process happen in such a fast manner that the time for heat to escape to the surrounding is very, very less. And the examples you have seen: bursting of tire, which is a sudden process; formation of clouds, the working of a diesel engine by adiabatic compression. Okay, all these are examples of adiabatic process. Now, hope that we'll be able to discuss adiabatic process in terms of PV diagram. You can see I have shown two diagrams here. Both are PV diagrams. So you can draw PV diagrams, PT diagrams, etc. But commonly we are using PV diagrams. I told you PV diagrams are also known as indicator diagrams in engineering. Now, if you notice the graph here, you can see two things. One is that I have drawn here, or I have represented here using gray lines a curve, or there are two curves to be precise. These two curves represents what is known as isotherms. We have seen that the isotherms are hyperbolic in nature. So this curve and this curve represents two isotherms. And hope you remember from our previous discussion that which of these, if you say that the temperature of this isotherm is T1 and the temperature corresponding to this isotherm is T2, hope you will be able to predict which one will be lesser or which one will be higher. And hope you remember our conclusion was the isotherm which is closer to the origin in a PV diagram will be having low value of temperature. So from the diagram we can see that T2 in my labeling is greater than T1. That is for sure. Right? Now, in the same diagram, I have represented another curve in red with an arrow. And this curve is what is known as an adiabat, or it is the graph corresponding to an adiabatic process. So, in the same PV diagram, we have represented two isotherms as well as one adiabat. Now, remember that all these graphs will not be in the same plane actually. We have got some limitation, I told you in the previous section, because it's a plane, PV is a plane, but we are dealing with three quantities: pressure, volume and temperature. So certainly all these, both of these graphs cannot lie in the same plane. Actually, to understand its real variation, you will have to use some three-dimensional model which is available in some of the standard websites or some of the standard textbooks. Three-dimensional pictures or three-dimensional models are also available. Think on that. Anyway, they are not in the same plane. For the time being, I have taken some projection of that graph. You can take it like that. I have taken a projection onto the PV plane. Okay. So now, what I want to tell you is that you compare the two curves here. One is the isotherm and the other is the adiabat. The thing to be noted is that the adiabat will be always steeper than an isotherm. This is something very, very important. An adiabat in a PV diagram will be always steeper than an isotherm. Suppose that isotherm is or you can say the adiabat is connecting two isotherms. So we have taken an adiabat which connects two isotherms. Okay, it is connecting two different isotherms, means that the temperature here for the first point, you can take it as the temperature of the first isotherm, which I have taken T1, but already it is named as Ti. I can say this is Ti. You can include a Ti also here if you need. Now the temperature of the final state of the system is you can say PF, VF, and you can, if you want, you can just mark it is T2 or TF, because here you have used a point on the second isotherm. So you can see an adiabat actually connects two isotherms. An adiabat is connecting two isotherms. The reason is well and clear, because during an adiabatic process there will be a change in temperature. Hope that idea is clear to you. And remember, the slope of an adiabat is always greater than the slope of an isotherm, or an adiabat will be always steeper than an isotherm. So that is one thing that I want you to understand and keep in mind. Okay. Another thing you can see when you compare the first graph and the second graph, one thing is clear, that in the first graph, you know, the arrow has been given in the upward direction. You know the reason, because this one has been taken as initial volume and this one is the final volume, and the final volume is less than the initial volume, and you know the process will be named as a compression as usual. And in the adjacent graph, you can see only the arrow direction has been reversed, means the process happens in this particular direction. Initially the volume is lesser, final volume is greater, so you know the process is representing an expansion, and the process is hence named as an adiabatic expansion. And we have already concluded that an adiabatic expansion results in cooling, as in the formation of clouds we have seen. So adiabatic expansion results in cooling and adiabatic compression results in heating. So now you can once again verify your concepts by using this by the conclusions, because this is an adiabatic compression. So the final temperature in adiabatic compression has been labeled now as TF or T2 here, and this T2 we have already concluded that that is greater than T1. So you can see that our concepts are matching. Okay, and the same way here you can see, you know, the temperature T2, this is T2, and this one is what, T1, right? Now what is the advantage? The process that is happening here is an adiabatic expansion. So you can see this is the final temperature, right? The final temperature in this case. Now in the case of you can see adiabatic expansion, the temperature should be what? The temperature should be lesser, and you can see here in this particular example, this isotherm is lying closer to the origin. So this isotherm, which I have labeled having temperature T2 or TF, should be having lower value, That is from our knowledge of isotherms, and also it is matching with the idea of adiabatic expansion, which should also lower the temperature. So you can see that the graphs that we have learned and the results that we have extracted from the graph are exactly matching with our concepts. So that's about the comparison of an adiabat and isotherm once you draw both in the same graph. So suppose that somebody has given you, this is your take home of the session, you have got a graph, and let this graph be a PV graph as usual. So we will take pressure along y-axis as usual and volume along x-axis, and suppose you are given two graphs, like no labeling other than the axis. You are given two graphs. Suppose this is one graph, it's a curve, and another graph, suppose that another graph is something given like this. Okay, we just neglect the curve that happens in the beginning. So this is graph A and this is curve B. Now suppose somebody asks you which of this graph represents adiabatic process and which will be representing isothermal process. I think you won't have any doubt at all, because you have already learned that an adiabat in a PV diagram will be always having greater slope. Actually the slope is negative, can't you see, because it is decreasing. So it's a negative slope, doesn't matter, you compare only the magnitudes. So adiabat will be having greater slope compared to an isotherm, or an adiabat will be a steeper curve compared to an isotherm. So you can clearly see that this graph B is steeper than the graph A. So the steeper curve will be labeled as adiabatic curve. So this is the adiabat, whereas the one having lesser slope will be the isotherm. So this is what we have to do. Is it not easy to identify the two curves? Now in the next session we will prove that an adiabat is, the slope of an adiabat is gamma times the slope of an isotherm. Okay, thank you.